Hey everyone, and welcome to this explainer. Today, we're stepping into the shoes of a molecular detective. If you spent any time looking at NMR spectroscopy, you know it is an absolutely phenomenal tool for mapping out the structure of a molecule. But there is one notoriously frustrating suspect that has baffled so many of us, and that is the unpredictable, wandering hydroxyl proton. Seriously, sometimes it shows up as a sharp peak, sometimes it's just this wide, blurry bump, and other times it seems to literally disappear completely. So why does it do this? And more importantly, how can we control it? Well, that's exactly the mystery we're going to solve today.
Okay, let's dive into this with what I honestly think is one of the most brilliant analogies in analytical chemistry. I want you to think of your NMR spectrometer not as some magical magnifying glass, but as a camera with a really slow shutter speed. Think about it. If you're trying to photograph a race car zooming by at top speed, and your shutter is open for a full second, what do you actually get? You just get a blur, right? You don't see the distinct shape of the car. You just get this time-averaged streak across your photo. Well, the exact same physics applies to the molecules inside your NMR tube. If a chemical event happens way faster than the spectrometer's shutter speed, the resulting spectrum just becomes completely blurred or time-averaged. So the really crucial thing here is understanding the numbers behind this shutter speed. The NMR timescale, which is the time it takes for a nuclear magnetic resonance transitional event to occur and actually be recorded, is typically about 10 to the negative 2 to 10 to the negative 3 seconds. Now that might sound incredibly fast to us, but let's compare that to our prime suspect, the hydroxyl proton in an alcohol. At room temperature, a pure liquid alcohol sample goes through intermolecular proton exchange at a rate of roughly 100,000, that's 10 to the 5th, protons per second. That proton is hopping on and off the oxygen atom way faster than the NMR can possibly snap the picture.
So, to troubleshoot this using our camera concept, here is our roadmap. First, we'll look at the wandering hydroxyl proton. Second, freezing the chemical action. Third, the deuterium disappearing act. Fourth, peak broadening. And finally, shifting shapes, also known as tautomerism.
Section 1. The wandering hydroxyl proton and its unpredictable chemical shifts.
Let's kick things off with our primary suspect found in alcohols. This thing is a classic headache because its chemical shift simply does not stay put. Depending on variables like the temperature of your sample, trace acidic or basic impurities, concentration, and your choice of solvent, the peak can wander anywhere from 0.5 all the way up to 5.0 parts per million. But the biggest culprit here? It's absolutely the extent of intermolecular hydrogen bonding. In a highly diluted solution where there's almost no hydrogen bonding, that proton might show up near 0.5 ppm. But in a concentrated solution where molecules are tightly packed and hydrogen bonding is everywhere, that peak shifts way downfield, pushing closer to 4 or 5 ppm.
For example, take an ordinary room temperature sample of ethanol. If you look for the OH peak, it shows up as just this broad, featureless singlet. Why? Because those hydroxyl protons are exchanging between ethanol molecules 100,000 times a second. So the NMR spectrometer essentially sees the proton as unattached more frequently than attached. That incredibly rapid chemical exchange completely decouples the spin interactions between the hydroxyl proton and the adjacent methylene protons. Our camera shutter is just too slow, so we end up with a time-averaged blur instead of clean, clear spin-spin splitting.
Moving to Section 2. Freezing the chemical action to slow down that exchange.
But you know, we're definitely not helpless here. If rapid chemical exchange is causing the blur, we can dig into our chemist toolkit and literally force it to slow down. If we take methanol at roughly room temperature, around 290 Kelvin, we just get two simple singlets. But watch what happens as you drop the temperature down to 200 Kelvin. Once you get below minus 33 degrees Celsius, or 240 Kelvin, the chemical action effectively freezes. We've managed to slow the proton exchange down so much that it finally fits within the timescale of our NMR shutter speed. Suddenly, almost like magic, that blurry OH resonance resolves into a beautiful, crisp quartet, and the methyl group becomes a clear doublet. We slowed the car down just enough for the camera to catch it in perfectly sharp focus. So dropping the temperature reveals all that hidden coupling. But honestly, sometimes revealing the coupling just makes a complex spectrum even more crowded and completely impossible to read. What if we want to go the entirely opposite route? How can we pull off a chemical magic trick to make a problematic overlapping OH peak just completely disappear from our view, totally cleaning up the rest of the spectrum? That brings us to Section 3, the deuterium disappearing act, or D2O exchange.
This is one of the most elegant and frankly most satisfying laboratory techniques in NMR spectroscopy. And the procedure is incredibly straightforward.
You literally just add a few drops of heavy water, D2O, to your NMR tube, cap it, and give it a really vigorous shake. After letting it sit for a few minutes to reach equilibrium, the rapidly exchanging acidic protons on your alcohol just effortlessly swap places with the deuterium atoms in the heavy water. Then you pop the tube right back into the spectrometer and rescan it. Because deuterium resonates at a completely different frequency than regular hydrogen, your problem peak simply vanishes.
And the visual proof for this is undeniable. If you run a sample of 2-chloroethanol before treatment, the OH proton is this broad, ugly resonance right around 2.22 ppm. And even worse, it's totally muddying up the adjacent methylene multiplets because of partial coupling. But after adding D2O, poof, the hydroxyl peak is virtually gone. It's reduced to this tiny, negligible signal. And look what happens to the methylene groups. Without that partial coupling from the OH proton interfering, they instantly clean up into these nearly perfect, super easy-to-read first-order multiplets. It is such a brilliant way to simplify messy data.
Section 4. Peak broadening, and what happens when we're caught in the middle.
So we've seen what happens when the exchange is incredibly fast, which gives us that single time average peak, and what happens when it's very slow, which gives us distinct split peaks. But what happens when the exchange rate is caught exactly in the middle, when the chemical exchange rate isn't lightning fast, but it's not totally frozen either? When it's on the exact same order of magnitude as the NMR shutter speed, we get severe peak broadening. As you transition from slow exchange to intermediate exchange, the distinct peaks actually lose their height and they widen dramatically at the base. They spread out because the spectrometer is actively struggling to decide if the proton is attached or unattached, essentially capturing it halfway through the jump. It's only when the exchange speeds back up to being very rapid that the blur coalesces back into a single, sharp time average peak. So rule of thumb, if you ever see a wide, squat peak in your spectrum, your chemical exchange is caught right there in that intermediate NMR timescale.
Section 5. Shifting shapes, also known as tautomerism.
Up until now, we've been completely focused on intermolecular exchange in the solvent. But what if the exchange is happening internally, inside the molecule itself? There are two main types of this shape-shifting, or tautomerism, to consider, and they act completely differently in front of our NMR camera. First is keto-enol tautomerism. In molecules like acetyl-acetone, the conversion between the keto form and the enol form is actually quite slow on the NMR timescale. Because it's slow, our camera easily captures both forms at the same time. You literally get the spectrum of the enol form superimposed directly on top of the spectrum of the keto form, and you can even calculate the equilibrium ratio just based on the peak sizes. But contrast this with valence tautomerism, like you see in the molecule bovalene. Here the molecule is rapidly shifting its internal covalent bonds. As you heat bovalene up to plus 120 degrees Celsius, this internal shifting becomes so incredibly fast that the NMR just cannot keep up. So instead of distinct peaks for the different hydrogen environments, the whole thing blurs together into one single sharp time average peak.
So, as we wrap up this molecular detective story, I want you to remember this core principle. Your NMR spectrometer is, in effect, just a camera with a slow shutter. Truly understanding that gives you so much power in the lab. By manipulating the temperature to freeze reactions, controlling purity and concentration to affect hydrogen bonding, or using heavy water to perform literal disappearing acts, you dictate exactly what that camera sees. You are absolutely no longer at the mercy of unpredictable chemical shifts or blurry broad peaks. So, the question is, how will you use these tools to capture the chemical mysteries in your own work? Thanks so much for joining me on this explainer, and happy experimenting.